Question 1A then is about the differences between the modern periodic table and Mendeleev's. Here are the answers you can give. Now that first bullet point where it says the modern table has more elements, you could give a reverse argument there and say Mendeleev's table had fewer elements. Now because you have to give the differences between the modern table and Mendeleev's periodic table, you need to comment on both of them. Now you don't have to do that for the first one, because when you say the modern table has more elements, that's a comparison already. But for the others, if you look at the second bullet point, it says the modern table, the modern periodic table, has noble gases. Well, then you have to then go on to state that Mendeleev's table does not have noble gases. So don't just leave it as the modern table has noble gases. The same with that third bullet point. You don't just say the modern table has no gaps. You need to go on to state what Mendeleev's table has, and it obviously does have gaps. He left gaps for undiscovered elements. Now, group 1 metals, or highly reactive metals, they're the alkali metals, and they would react with water and with oxygen in the air, so they have to be stored in oil. And part 2, before you would react lithium or any alkali metal with water, 2 safety precautions that we would take, apart from safety glasses, but safety glasses are sort of a given. Now, the reaction itself is quite vigorous, so we should use a safety screen. A second point would be to use a small piece of the metal. It's a highly reactive metal, so we don't want to touch this with our skin. So use tongs. Another point would be to use a large volume of water. This reaction gives out a lot of heat. That can be dangerous. So if we use a large volume of water, that will absorb that heat and just makes it more safe. When alkali metals react with water, a metal hydroxide, so in this case it's lithium hydroxide, and hydrogen are produced. It needs to be balanced, so I put a 2 in front of the Li, in front of the H2O, and in front of the LiOH. This here is an alkaline solution. They're known as the alkali metals. And it would turn phenolphthalein indicator pink. It goes pink in alkaline solutions. On to part C then. Physical properties of the halogens. Again, this is just a recall. Chlorine is a green gas, or you could say a yellow-green gas, not yellow on its own. Bromine is a liquid. It's one of 2 liquids in the periodic table, the other one being mercury. And then iodine is a solid at room temperature, and it's a grey-black solid. The balanced equation then of the reaction between chlorine and potassium iodide, well, chlorine, all of the halogens, when they're on their own, are diatomic. So 2 atoms covalently bonded together. So it's going to be Cl2. Potassium iodide solution is going to be Ki. Now chlorine is more reactive than iodine. The halogens get more reactive as you go up the group. So the chlorine will displace the iodine and form potassium chloride. And then iodine is produced. So it goes from iodide to iodine. That needs balanced. That's it. Now, if you were asked to state the colour change, well, potassium iodide solution is colourless, because it's a solution of a group 1 compound. And because you're getting iodine produced, when iodine is in an aqueous solution, it's brown. So the colour change here would be colourless to brown. The half equation then of the chlorine molecule. So we start off with the chlorine molecule. Now it's going to KCl, you can see that over here. So that's a chloride ion. Now we need to balance that. We have two chlorines on the left, so we need to put 2 in front of the Cl minus on the right hand side. Now half equations always contain E minus, either on the left hand side or on the right hand side of the arrow. Now if you look at this, you can see that it goes from Cl2, there's no charge there, that's neutral. And on the right hand side it goes to 2 Cl minus. So that means that the Cl2 must gain 2 electrons. That's a balanced half equation. Okay, question 2a is another recall question, a definition. A strong acid is completely ionized in water. An example would be HCl, that's a strong acid, and it completely ionizes into the ions hydrogen and chloride. If you had sulfuric acid, which is H2SO4, that would completely ionize into 2 hydrogen ions, so 2H plus, because it's H2, and then you have your sulfate ions. A weak acid only partially ionizes. So if we were doing an equation for a weak acid, we would use a reversible arrow. So an example, I'll just do it up here, would be ethanoic acid that you would find in vinegar. So that's the formula of ethanoic acid. I use a reversible arrow, and then I have my H plus, because it's still an acid. Remember, acids are substances that produce hydrogen ions in solution. And if this H gets released, then that leaves us with CH3COO minus, that's ethanoate. So that's the equation to show the partial ionization of a weak acid. Okay, then on to part 2. Blue litmus in acid is going to be red, and with ammonia solution it's going to be blue. Ammonia solution is alkaline. Phenolphthalein in an acid is colourless, and in an alkaline solution it's pink. B part 1 then, we'll have to write a balanced simple equation for the reaction of ammonia with nitric acid. Now ammonia is NH3 and nitric acid is HNO3. Now even though this is an acid and an alkali reacting, we don't get a salt and water the way we do with an acid plus an alkali gives a salt plus water. When ammonia reacts with an acid, you just combine the two reactants. And so what you get is NH4, which is ammonium, and NO3. So that there is known as ammonium nitrate. On to part 2 then. How could we show practically that the reaction is exothermic? Well, an exothermic reaction gives out heat. And the way we would measure that would be to use a thermometer, and we would see an increase in the temperature. I see part 1 is asking for the ionic equation for neutralization. Again, this is just a recall question really, because it doesn't matter what the acid and alkali are, it's the same ionic equation. Acids produce hydrogen ions. Alkalis, which is what calcium hydroxide is, produce hydroxide ions. And when those two combine, they form water. Now the question also asks us to give state symbols. Well, the hydrogen and hydroxide ions are dissolved in water to start with, and water itself is a liquid. Calcium hydroxide is more commonly known as lime water. And that's the solution that's used to test for carbon dioxide gas. You bubble the carbon dioxide gas into it and it goes from colourless to milky. Okay, D1 then is just an equation for the reaction between a carbonate and an acid. That'll give a salt plus water plus carbon dioxide. And then part 2, you have to describe how you'd obtain pure, dry crystals of calcium nitrate. Now the method for making all these are very similar. So you just have to sit and learn them off. If you can learn one of them off really well, as I said, the rest of them have a very similar pattern. So we've placed the nitric acid into a beaker, or it could be a conical flask. And if you wanted to include a volume there, we generally would use about 30 cubic centimetres up to 50 cubic centimetres. The next stage would be to add the calcium nitrate until the reaction stopped. We would know when the reaction stopped because there'd be no more fizzing. When a carbonate reacts with an acid, there'll be fizzing because carbon dioxide gas gets given off. Or you could say that solid remains. Because again, when you react the calcium carbonate with the nitric acid, it reacts and disappears. So when it stops disappearing, you know that all of the acid has been used up. And that is an indication that the reaction has stopped. We now have to get rid of that excess solid, the solid that has not reacted. So you'll do that by filtration. So you can see the diagram on the right hand side. You don't have to draw the diagram, it's just done here so you can see more clearly of what's happening. The unreacted calcium carbonate will get trapped in the filter paper. Remember, that's known as the residue. And then the calcium nitrate solution will filter through and go into the evaporating basin. We now want to evaporate half of that liquid, because then that, as it cools, the solubility of the calcium nitrate will decrease. So while there's a large volume of water, the calcium nitrate will want to stay dissolved. So if we remove or reduce some of that volume, and as the temperature decreases, the calcium nitrate will not want to stay dissolved, so the solubility decreases. We don't evaporate at all, because if we did that, we wouldn't end up with crystals. We would just end up with a solid or a powder. So once we've evaporated half, we'll leave the rest to cool and crystallise slowly. The crystals will have formed. We then can filter that, because often there's some liquid left over. So you could filter that, or you could just dry the crystals between pieces of filter paper. Now don't say dry between a piece, one piece. It has to be pieces or two pieces. And we don't say a paper towel. Okay, it has to be filter paper. Question 3 then, part A. So carbon has several allotropes. Graphite, diamond, graphene. And an allotrope is just different forms of the same element in the same state. So graphite is one of those allotropes. So what we've got to do then is draw the carbon atoms. And remember, graphite is made up of hexagonal rings. So something like that would do. So you can see each carbon atom, and it's a labelled diagram, so we've got to label all of this. Those solid lines are covalent bonds. Those are very strong, and that's the reason graphite has a very high melting temperature. I've got to show another layer. Now that would do. I'm just going to put in another hexagonal ring. Now there are weak forces of attraction between those layers, which is why the layers can slide over each other. And those are known as van der Waals forces. So there's a structure of graphite. Hexagonal rings. We've got the carbon atoms labelled, the covalent bonds labelled, the weak van der Waals forces, and then we've shown that it's made up of layers. I've already mentioned why graphite has a high melting point. That's due to the strong covalent bonds that require a lot of energy to break. Okay, part B then should be fairly straightforward. A carbon atom has an atomic number of 6, and the atomic number equals the number of protons in an atom. An oxide ion, well, that comes from oxygen. So I'm going to put in O to start with. Now, an oxygen atom has 8 protons, so that means an atom would have 8 electrons. But this is an oxide ion. So an oxygen atom needs to gain another 2 electrons to get a full outer shell. So that would mean that the ion has 10 electrons. So that would make the charge 2 minus. And then the final particle, well, the number of protons are 13. That's the atomic number that identifies the element. That's aluminium. And you can see that the electrons do not equal the protons. So this has to be an ion. Anytime the protons and electrons are unequal, it's an ion. Well, you've got 3 more positive charges. So 13 protons, 10 electrons. So that means it's going to be Al3+. So this is an aluminium ion. And then part C is where you just have to draw a molecule of carbon dioxide. Remember, there are 2 molecules that contain a double covalent bond. One is oxygen, the other is carbon dioxide. So I'm going to draw the carbon atom, and then 2 molecules of oxygen. Carbon has 4 electrons in the outer shell, and the oxygen has 6. 1, 2, 5, 6. And do the same on the other side. 1, 2, 3, 4, 5, 6. So there we are. So you can see in the overlap there are 2 pairs of electrons, 2 double bonds. In part D, you have to describe a metallic bond. This applies to all metals. And I'll draw out the diagram of a metallic bond. Now you should be able to picture this in your minds. So that's why it's good to associate pictures or images with the theory. You'll remember it better. So there we have our metallic bond. These are positive ions, and then we've got these delocalized electrons. So you can see it's a regular pattern. We say it's a regular lattice. So the definition itself is the attraction between delocalized electrons and a regular lattice of positive ions. For part 2, malleable just means that the metal can be hammered into shape. And an explanation for this is that the layers of ions can slide over each other without disrupting the structure. So it's still a metallic bond, just the different ions have moved across, but it still maintains that lattice and the attraction between the positive ions and the delocalized electrons. And in part 3, aluminium can be used in bicycle frames because it has a low density. Question 4 then is about solubility. So we have to determine if the solution containing 680 grams of the potassium iodide and 500 grams at 20 degrees C is saturated or unsaturated. So 680 grams in 500 grams of water. Now, solubility is always expressed in terms of grams of solid that dissolve per 100 grams of water. And you can see that here. So we're looking at 20 degrees C. And we can see that 144 grams of the solid dissolve in 100 grams of water. So then we scale this. Now, we can either multiply the 100 grams of water by 5, in which case we multiply the 144 grams by 5. Or what we can do is divide this by 5. If I divide that by 5, that'll now turn it into 100 grams of water. So that would mean then that I have to divide the 680 by 5. Now if I divide 680 by 5, I get 136 grams. So just go over that wee bit again. If you have 680 grams at 20 degrees C, and that's in 500 grams of water, that's equivalent to 139 grams in 100 grams of water. Now from the table, we need to have 144 grams per 100 grams of water to make the solution saturated. So 20 degrees C, it's possible to dissolve a maximum of 144 grams of potassium iodide to make the solution saturated. Now we have just worked out that in this example, 680 grams per 500 grams of water is equivalent to 136 grams per 100 grams of water. Well, 136 is lower than 144. So this solution is going to be unsaturated. In part 2, I can see here that the temperature is 30 degrees C. So I'm going to use this row. And at 30 degrees C, it's possible to dissolve 152 grams of solid. So in this next part is if we have 25 grams of water and it dissolved a further 4 grams of potassium iodide, we've got to have the same mass of water. So I'm going to multiply this by 4, and that will bring the water up to 100 grams. That means I have to multiply this by 4. That'll be 16 grams. This is still at 30 degrees C. Now, a few moments ago we worked out that at 30 degrees C, 152 grams of potassium iodide dissolved per 100 grams of water. We have now worked out that at a higher temperature, this solution dissolved 16 grams per 100 grams of water. That's what we've just worked out here. So that then gives a total of 168 grams. And this is now per 100 grams of water. If you look at the table, you can see that in order to dissolve 168 grams of solid per 100 grams of water, the temperature has to be 50 degrees C. Potassium iodide solution is colourless. It's a solution of a group 1 compound. It's always colourless. Now we're going to describe how the flame test is carried out. Well, you need to use a nichrome wire. It doesn't produce a colour of its own. It's going to be dipped into concentrated hydrochloric acid. This then is placed into the sample and into a blue Bunsen flame. And we use a blue flame because it's a very faint colour, so any colour that's produced will be seen easily. If you used the luminous or the yellow flame, that would mask the colour that the metal compound would produce. And now we have to state the expected result. Well, this is potassium iodide, so potassium ions would produce a lilac flame. See part 1 then, a chemical test to identify iodide ions. Halide ions are identified using silver nitrate solution or aqueous silver nitrate. Always. And again, you've got to just get that into your mind. Iodide, bromide, chloride, use silver nitrate solution. Now, the other thing to remember is that this is a solid sample. Before we use a silver nitrate solution, we've got to dissolve the sample in water. That's often overlooked. When you're doing a flame test, you don't dissolve it in water. You use the solid sample. But when you're carrying out any of the chemical tests, then you do have to dissolve in water. Then add silver nitrate solution. And don't forget solution, not just add silver nitrate. And if it has an iodide, it will produce a yellow precipitate. Remember, a precipitate is a solid that forms in a liquid during a reaction. Now, the balanced ionic equation for this, all of these reactions of the halides with silver nitrate follows a very, very similar chemical equation. We've got silver ions react with the halide ions. In this case, it's iodide. And those are both aqueous. It means they're dissolved in water. We don't have to include aqueous. The question doesn't tell us to include state symbols, so I'm going to leave them out. But both of these ions would be dissolved in water. But when they combine, they produce silver iodide, which is the yellow precipitate. Question 5, part A, is a definition. Relative atomic mass. Then it's just the mass of an atom compared to the mass of carbon-12, which has a mass of exactly 12. Empirical formula is the simplest whole number ratio. So can we divide this any more? Well, 3 goes into 12 4 times. And the 12's outside the bracket, so that means we've got 12 carbons and 12 oxygens. So the empirical formula is Fe, and we just have 1 because we're dividing by 3. Then it's going to be C4O4. The formula then of this hydrated salt Well, hydrated salts always have a formula, a dot, and then whatever number of moles of water. Iron 2 sulfate is FeSO4. We put a dot, and we're told there's 7 moles of water crystallization, so it's going to be 7H2O. And to work out the percentage of water crystallization, we've got to work out the total mass of the water. That's 7 times 18. And then we divide that by the total mass of the hydrated salt. In this case, it's 278. And that works out to be 45.3%. Here we've got a reactant mass calculation. Now we're trying to calculate the mass of iron, that's this part, obtained when we use 16,000 kilograms of the iron oxide. I'm just going to write that out again here. So you can see right away it's a 1:2 ratio. Now, the 16,000 kilograms, whenever we work out moles, it's always the mass in grams. So I'm going to write down 16,000 kilograms. To convert that to grams, multiply by 1,000. And then I divide by the RFM of Fe2O3, which is 160. And that gives 100,000 moles. Now you can see it is a 1:2 ratio, so that means that that should produce 200,000 moles of iron. Now let's convert that to a mass. So the mass of iron is going to be 200,000 times the RFM of iron, which is 56. You don't do 2 times 56. The balance of numbers are just there to work out the ratio of moles. And so that works out to be 11,200,000 grams. Now we want that in tons. Well, 1 ton is equal to 1 times 10 to the power of 6 grams. So if we move the decimal place 1, 2, 3, 4, 5, 6 places, that's 11.2 tons. To work out the percentage yield, that's the actual yield over the theoretical yield. So when you work out the calculation from the previous step, that's the theoretical yield. And we multiply that by 100. That gives 91.1%. And then the final question is where we have to calculate the empirical formula. So we write down the symbols for the elements. So we've got iron, sulfur. Even though we've been given percentages, we just treat them like masses. So we've got 46.5% or grams for the iron, and then we're going to divide that by the RFM, which is 56, and that gives 0.83 moles. We do the same sort of thing for the sulfur. We've got 53.5% or 53.5 grams, divide by the RFM, and that gives us 1.67 moles. We then divide through by the smallest number, and we get a 1:2 ratio. So the empirical formula is FeS2. Remember, when you divide by the smallest number, if you end up with one of these values being a 0.5, then you multiply both of them by 2. If, when you divide through by the smallest one, you end up with a 0.33 or a 0.66, you would multiply both of them by 3 to bring them to a whole number. But in this case, we didn't have to do that. It was a nice 1:2 ratio.